vast universe, death is often not an end, but a transformation. Sometimes creating entities even more magnificent and terrifying than the life that gave birth to them. Our story begins here, not with the birth of a star, but with its glorious departure. Consider a giant star, a fire god in the galaxy. With a mass 8 to 20 times that of our Sun. For millions of years, it was a great nuclear reactor, a beating cosmic heart, continuously fusing lighter elements into heavier ones. Hydrogen turning into helium, helium into carbon, carbon into oxygen, and so on in a symphony of elemental creation. At its center, pressure and temperature reach unimaginable numbers. And it is this relentless battle between the immense gravity trying to crush the star and the radiation pressure from nuclear reactions pushing outward that maintains its delicate balance. But everything has limits. This battle cannot last forever. When the chain of nuclear fusion reaches the last element it can efficiently create, iron, the star's doom has arrived. Fusing iron does not release energy. On the contrary, it consumes energy. The star's nuclear heart, the energy source sustaining its life, suddenly stops beating. The outward radiation pressure vanishes in an instant. In that moment, gravity, the star's sworn enemy, wins brutally. With nothing to oppose it, the star's iron core begins to collapse under its own immense weight. In just seconds, a mass of matter the size of Earth is compressed into a sphere only a few dozen kilometers in diameter. The speed of this collapse is unimaginable, reaching nearly a quarter of the speed of light. This sudden collapse creates a shockwave, a massive blast wave, rebounding from the newly formed superdense core. This shockwave is energized by a storm of neutrinos, nearly massless fundamental particles, rushing outward with unstoppable force. It tears apart the star's outer layers in an explosion whose brightness can outshine an entire galaxy. This is a supernova explosion, one of the most spectacular and violent events in the universe. As the dust and gas from the explosion dissipate over thousands of years, leaving behind a beautiful but ghostly nebula, what remains at the center of the disaster scene is something that almost defies all conventional physics. It is the corpse of the collapsed star. It is a neutron star. And here is where normal science ends and madness begins. A neutron star is a paradox. It is one of the smallest objects known to astronomers, yet simultaneously one of the densest and most powerful objects. To understand its strangeness, we must abandon all conventional concepts of matter, space, and gravity. Let's start with its most prominent characteristic, density. The core of the parent star has been crushed to an almost incomprehensible degree. A typical neutron star has a mass about 1.4 times that of our Sun. However, this entire immense mass is compressed into a sphere only about 20 kilometers in diameter. What does this mean in practical terms? It means that a teaspoon of matter from a neutron star would have a mass of about 6 billion tons. This is equivalent to compressing the entire mass of all humans on Earth into a space the size of a sugar cube. Mount Everest, if made of neutron star matter, would be only as small as a grain of sand. With the mass of a sun compressed into such a small space, the gravitational field on the surface of a neutron star is extremely terrifying. It is about 200 billion times stronger than Earth. If you could, though certainly cannot, drop an object from a height of 1 meter above the surface of a neutron star, the object would plummet and hit the surface in just 1 microsecond at a speed of about 7.2 million kilometers per hour. The gravity is so strong that it can significantly bend the path of light. If you stood on the surface of a neutron star and looked straight ahead, you could see the back of your head because light from there is bent around the star and enters your eyes. The surface of a neutron star is also extremely flat. Any mountains on the surface cannot be more than a few millimeters high. Anything taller would be flattened immediately by the immense gravitational field. Its gravity creates a gravitational well so deep that, to escape from the surface of a neutron star, you need to reach an escape velocity of about 100,000 kilometers per second, which is about 1/3 the speed of light. compared to Earth's escape velocity of only 11.2 kilometers per second. The fundamental principle in physics is the conservation of angular momentum. The original neutron star, with a diameter of millions of kilometers, could rotate quite slow, possibly taking several days or weeks to complete one rotation. But when its core collapses from Earth's size down to just 20 kilometers, like a figure skater pulling in their arms, its rotation speed increases dramatically. As a result, a newly formed neutron star can rotate hundreds of times per second. The speed at its equator can reach a significant fraction of the speed of light. Over time, this rotation speed will slow down as the star loses energy. But even old neutron stars can rotate several times per second. If density, gravity, and rotation speed aren't crazy enough, the magnetic field of a neutron star takes everything to a new level. The collapse process also compresses and amplifies the magnetic field of the pair. The result is a magnetic field so strong it's unimaginable. Earth's magnetic field is about 0.5 Gauss. Gauss is the unit for measuring magnetic flux density. The surface magnetic field of a typical neutron star is about 10 to the power of 12 Gauss. That is, 1 trillion Gauss. If such a neutron star came close to Earth at the distance of the Moon, its magnetic field would destroy the atomic structure of metal, turning metal objects into clouds of plasma. It would make your compass not only point north, but also tear apart the iron atoms in your blood. And that's just a normal neutron star. We will soon meet a special type called a magneton, with a magnetic field 1,000 times stronger. The surface of a neutron star is already a strange place. But what lies beneath it? Exploring the internal structure of a neutron star is like a journey into a land where normal physical laws are bent and broken. Scientists cannot observe the inside directly, so they must rely on theoretical models and indirect observations. This is our best picture of the layered structure of a neutron star. From the outside in. First layer, atmosphere and outer crust. Although it seems unreasonable for such a dense object to have an atmosphere, but it does exist. It is a superheated plasma layer, only a few centimeters to 1 meter thick, compressed by immense gravitational force. Its composition depends on the star's temperature, but mainly consists of hydrogen, helium, or carbon. Beneath this thin atmosphere lies the outer crust. The outer crust is about a few hundred meters thick, consisting of atomic nuclei, primarily iron and other heavy elements, completely ionized, and free electrons moving between them. Due to the extreme pressure, these nuclei cannot exist in gas or liquid form. Instead, they are compressed into an extremely hard and dense crystalline structure, similar to a metal crystal lattice, but billions of times stronger. This may be the hardest material in the universe. The second layer, the inner crust and core. As we go deeper inside, the pressure increases to the point where the nuclei begin to touch each other. Here, a strange phenomenon occurs. The neutrons inside the nuclei begin to leak out and exist freely. We have a mixture of nuclear clusters immersed in a sea of free and superfluid neutrons. In this transition region, nuclear repulsion and surface begin to compete with the electrostatic repulsion between protons. This causes the nuclear clusters to no longer be perfect spheres. Instead, they can be stretched, merged, and deformed into strange structures that physicists call by a very evocative name, nuclear pasta. Depending on density and pressure, the nuclei can form structures like spaghetti, long strands, lasagna, flat sheets, or even gnocchi, clusters. These structures, although sounding delicious, represent one of the most bizarre states of matter ever theorized. Beyond the crust, we enter the neutron star's core, which makes up most of its mass. The outer core is an almost pure ocean of neutrons. Here, the concept of atoms completely disappears. In this extreme environment, neutrons behave as a quantum fluid. More specifically, they form a superfluid with no viscosity, meaning it can flow without friction. Once excited, it will flow forever. The remaining protons, about 5%, also pair up to form a superconductor, allowing electric current to flow without resistance. The superfluid neutron ocean, mixed with superconducting protons, forms a state of matter not found anywhere else. It is here that a new force emerges to resist gravitational collapse. It is not thermal pressure like in a normal star, but neutron degeneracy pressure. This is a purely quantum mechanical effect, described by the Pauli exclusion principle, which states that no two neutrons or any other fermions can coexist in the same quantum state. When you try to compress neutrons together, they resist fiercely. This resistance is strong enough to prevent a star heavier than the Sun from collapsing further. Finally, the fourth layer, the inner core, the heart of the mystery. As we approach the center of the core, the pressure and density become so great that even our most advanced physical models begin to fail. This is the true frontier of human knowledge. Scientists are not 100% certain about the state of matter existing here, but there is one most compelling possibility: quark matter. Neutrons, like protons, are not fundamental particles. They are made up of smaller particles called quarks. The pressure in the inner core is so strong that it can break apart the neutrons themselves, releasing their constituent quarks. The neutron star's core could be a sea of free quarks. Not all neutron stars are the same, like living organisms. They evolve, change, and express themselves in very different ways. We can observe them in many forms, primarily consisting of two main types: pulsars and magnetars. Pulsars are the most precise clocks in the universe. Their regularity can rival and sometimes surpass even our most sophisticated atomic clocks. This stability allows scientists to use them for extreme physics experiments. For example, by tracking the tiniest signals from pulsars in binary star systems, scientists found the first indirect evidence of gravitational waves. Unlike pulsars, magnetars are furious monsters. They are a rare and much more terrifying type of neutron star, defined by a single characteristic: their magnetic field. While a typical pulsar has a magnetic field of about 10 to the power of 12 gauss, a magnetar has a magnetic field 100 to 1,000 times stronger, reaching up to 10 to the power of 15 gauss. This is the strongest magnetic field known to exist in the universe. This number far exceeds anything we can create on Earth and challenges the limits of physical theory. This magnetic field is so strong that it completely dominates the behavior of magnetars. The enormous energy stored in this magnetic field is the source of extremely violent energy outbursts. The surface of a magnetar is unstable. Its solid crust is constantly under pressure from the changing magnetic field beneath. Sometimes this tension becomes too great, causing a starquake that cracks the crust. This event releases a tremendous amount of energy in the form of X-rays and gamma rays in an explosion. The energy released in just a tenth of a second is equivalent to the total energy our Sun emits over 100,000 years. Magnetars are natural laboratories for studying physics under the most extreme conditions in the universe, where quantum mechanics and general relativity meet. They are living proof that the universe is capable of creating entities even stranger than we can imagine.